All right, can you hear me? So thank you very much, first of all, to the organizers for inviting me to speak at this fantastic conference. It's been a great pleasure. So I'll talk about F-theory and AdS3 CFT2, which sort of came out of a sociological experiment, putting AdS CFT people together with F-theorists. And so you can see here the people involved in this project are Chris Cousins, Daria Martelli, who are on the supergravity side, and then Craig Laurie and Jenny Wong, who are more on the F-theory side. And this is sort of, in case you don't know these people, these are the collaborators. And there's some earlier work together with these three gentlemen related to the field theory side of what I'll talk about. Okay, so let's start with some motivation. Why would we care about strings coming from D3 brains in F-theory? So this is what I'll talk about, and their holographic AdS3 duals. First of all, it's a strings conference, as someone noted earlier, so we should care about strings. Now, as an F-theorist, actually, these are very natural objects to study. So let's actually first recap what F-theory is. So it's type 2B with varying axial dilaton. Tau is the complexified combination here. And usually we consider this theory on an elliptically fibered Calabi-Yau n-fold. So there's an elliptic fiber whose complex structure is the axial dilaton and some base, which is the type 2B compactification space. And usually we get a minimally supersymmetric theory in even dimensions. So what have been the latest developments in F-theory? Well, first of all, there's been lots of progress in 6 dimensions. We heard some of that in the last talk. From an F-theoretic point of view, what's been really exciting is that F-theory actually, on Calabi-Yau 3-folds, can help classify 61,0 theories. There's been a lot of progress also in 4 dimensions, but I think most of that will be relegated to next week's String Pheno conference. I think there's no phenomenology talk at this conference here. And then actually something that's sort of started in the last year, 2-dimensional F-theory vacuum coming from Calabi-Yau 5-folds. So you put F-theory on a Calabi-Yau 5-fold, you get to 2 dimensions, and can study what type of theories we get here. So why would we study D3 brains in this setup? Well, we're looking at specifically wrapped D3 brains. So they'll be wrapping a curve inside the base manifold. In 6 dimensions, these are, of course, extremely important. They're like the diagnostic for the superconformal invariance of these theories, the tensionless strings. In 2 dimensions, in fact, this is where we sort of came to this problem. Actually, D3 brains are vital for the global consistency of the model, namely, there's a tadpole cancellation. The class of this curve that the D3 brain wraps has to cancel the 4th Chern class of the Calabi-Yau 5-fold and some contribution from the flux. So you're actually forced to have these D3 brains in your model. So the first, so here's a cartoon. There's an elliptic fiber. This is the base. This is the Calabi-Yau. And the D3 brain will wrap a complex curve inside the base, and some transfers R11. So there's a natural question: how do I characterize these 3 brains, these wrapped brains? What type of 2-dimensional theories do I get? And thirdly, these are actually conformal. What are the AdS3 duals? And this will happen actually within F-theory. So if you're actually an AdS CFT person, this is sort of the cue why this should be maybe of interest. So after 20 years, it's still exciting to find, and actually possible to find, new solutions. There's been a lot of progress in higher dimensions, but here I'll focus on AdS3. Of course, in the first Malacena paper already, there's an AdS3 solution, dual to, giving rise to AdS3 times the 3 times D4 solution, dual to D1, D5. What we'll look at more is D3 brains. And also here in type 2B perturbative string theory, there have been solutions by Kim and Benini-Bobov. So what we'll do is actually consider a generalization of this last class, coming from wrapped D3 brains, but where we allow some additional F-theoretic ingredient. So how has F-theory actually talked to AdS CFT? There have been lots of sort of similar setups. I think I want to maybe focus, sort of pointing out a few of them. These F-theory at constant couplings have been studied. They give rise to AdS 5 times S5 duals. They're sort of also F-theoretic in some way, but they're at constant coupling. Then, of course, the 61,0 series have AdS7 solutions in M theory and type 2A. So these are not really type 2B solutions dual to these 60 theories. What we'll consider here is these two-dimensional 0,2 or 0,4 theories arising from these three branes that are dual to AdS3 times S3 times B, and B is not going to be Calabi-Yau. So this is sort of the new type of solution we'll consider. So the plan is I'll first discuss a little bit what these two-dimensional theories are, then the AdS3 solution, and as an application, what we can compute and compare. So in AdS CFT, we'd like to always have something where we can calculate on both sides and actually compare. So here, this is sort of the first step is just computing the central charge. Okay, so how do we study these D3 branes in F theory? So let's just recap these three brane carry in flat space, the n equals 4 Supergravity theory, and embedded in type 2b, the axial dilaton is actually identified with the complexified coupling theta and G-Mills square. So in perturbative type 2b, I can also look at this problem of wrapping a D3 brane on a curve inside a Calabi-Yau, and I get a two-dimensional CFT transverse in R11. So to actually describe this problem, I need to topologically twist the theory along the curve. And so usually we take the SO1, 3 Lorentz and break this into SO11, acting on the R11 times U1C, and then twist that U1C with a U1R symmetry subgroup inside SU4. And if we now collapse the curve, we actually get a sigma model into the BPS equation moduli space, which here is the Hitchin moduli space. So how does this change this picture when we actually look at an F-theoretic setting? So I said tau is identified with the complexified coupling. So here, tau will now vary consistently with the SL2Z duality symmetry of type 2b. So tau will actually undergo some monodromies, A tau plus B over C tau plus D. So the interesting additional sort of thing that happens here is that under SL2Z, the supercharges actually also transform. And so they actually undergo a rotation by phase here. E to the I alpha is defined in terms of this duality element in SL2Z, so A, B, C, D are integers with the determinant here being 1. And this phase is determined in this way. And the whole thing also acts on the fields of, say, abelian Supergravity theory in the following way. The scalars are invariant. The fermions transform with the same phase as the supercharge. And this combination of the field strength transforms with the phase E to the I plus minus alpha. So this charges can also be identified with the abelian n equals 4 Supergravity theory with what's called the bonus symmetry of the n equals 4 theory. So if we actually consider now these three branes wrapped in the base of a Calabi-Yau, we actually need to also account for not just the curvature of the complex curve, but also this transformation under this U1D or duality. So this sort of topological twist, which was invented by Luca Martucci a few years ago, goes under the name of topological duality twist. So we take the U1D, the U1C, and twist this with a U1 inside the SU4R. So what it means for the fields is, as we'll see in a second, the fields actually then become sort of sections of line bundle where the line bundle has a connection which actually depends on the variation of tau. So it's 0 if tau is constant, so we don't see it in the standard type 2b setting, but here we see sort of a non-trivial transformation if tau varies in F theory. So this setup actually one can study in very big detail for the U1 symmetry gauge group, but actually it's useful to dualize this to M5 branes and look at sort of an M5 brane picture. So what does this sort of actually do, this strange new topological duality twist? So let's recap the 62,0 theory on elliptic curve times R4 is just n equals 4 Supergravity on R4 with a coupling tau, where tau is again the complex structure of the elliptic curve. So if we now look at the 62,0 theory on an elliptic vibration, so just an elliptic surface, let's call this here C hat, then this should correspond exactly to this 4-dimensional n equals 4 theory, where tau now varies over this curve. So the D3 branes indeed, from this setup here, under MF duality, map to M5 branes that wrap the elliptic fiber restricted to this curve. So this is a complex surface times R11. So in M theory, we'd be looking at M5 branes on a surface of this very specific form. And so what we can actually show is that this new twist here amounts to just a topological standard twist on a Kähler manifold of the 62,03. And this has some advantage because we can sort of now guess also how we might actually non-abelianize this theory. Okay. So this is just sort of a brief way to see that. So the 60 theory has these symmetries, and then we do the standard decomposition on Kähler surface into the U2 on the Kähler surface, and the SP4R R symmetry into SU2 times U1. And then this twist here is exactly the twist we would use, for example, like in the MSW string case, to define the theory on a Kähler manifold. And then we can look at what exactly this means in terms of the spin connection of the elliptically fibered Kähler surfaces. So if the Kähler surface specializes to something like this object here, then this connection here is exactly given in terms of this duality connection. Okay. So in F theory, of course, the elliptic fiber Calabi-Yaos, they're not just interesting when they're smooth, they're of course only interesting when they have singularities, which correspond, of course, to 7 branes. So in addition to this D3 brane having this elliptic fiber above it, there's also an intersection at points now with a discriminant locus where 7 branes are coming in. So I should make a small comment here that the types of strings that were discussed in the last talk, they correspond to more like the D3 brane actually being embedded into the discriminant locus. Here, I'll consider sort of this transverse intersections where we have point-like intersection between the D3s and D7. So what actually we obtain here at these intersections are additional modes, which are 3-7 strings. In the M5 brane dual, these correspond to additional modes coming from the reduction of the M5 brane theory on these singular fibers. So the singular fibers have additional 1-1 forms, and we can reduce now the 3 form or the 2 form, the Salto 3 form here along these 1-1 forms and get chiral modes that are localized at these points. And so these are exactly what we would call duality defects. So they're point-like, and as we encircle them, we undergo an SL2Z monotony dictated by the singularity. Okay, so let's actually look at an example. F theory on Calabi-Yau 3, elliptically fibered, and we look at this 4 to n equals 4 sub-Young-Mills on a curve times R11. Or in the dual M5 brane picture, we have a Calabi-Yau 3-fold, and we wrap in the elliptic fiber over a curve an M5 brane. So actually, the M5 brane picture is a little bit easier. If we look at this decomposition, we get the self-2 form, the scalars and the fermions, as well as the supercharges, decomposed in this way. We do this topological twist that I explained earlier, and we get 0,4 supersymmetry. If we did the same thing for Calabi-Yau 4 or 5 folds, this would give rise to 0,2 series. So this twist has also the effect that now actually the fields, carry these charges under this U1 twist and actually become sections of H01 of the surface or H10. So we now look at the spectrum of the theory in terms of the cohomology of this elliptic surface C hat. So this is the elliptic curve over C fibered. Actually, we can compute now the cohomologies of such an elliptic fibration, where in the standards of Weierstrass representation, F and G are sections of certain line bundles. And the line bundle is exactly given in terms of the restriction of the canonical, anti-canonical bundle of the base of the Calabi-Yau to the curve. And so the spectrum actually then takes the following form. We have always everything written now in terms of intersections of the curve with itself and the base, or the C1 of the base with the curve. And then the last line here is sort of this additional the additional modes which come from the H11, which are the 3-7 strings in the type 2b description. Okay, so putting it all together, and this will be what we'll compare at this later in the dual AdS3, we get the central charges for this model, which are given in terms of the self-intersection of C and C1 of B dot C. So I put here in sort of yellow, so you cannot see it, an N. So as you might have noticed, this was actually so far only for a single M5 brane or a single n equals 4, abelian n equals 4 Supergravity theory. So this actually would be very interesting to generalize it to SUN Supergravity theory and study that. So this actually has not been done yet and would, I think, be very useful, in particular in the comparison to what I'll tell you in a moment. Okay, so one small, okay, I will skip this here. One small comment. So I said in the type 2b setting, the two-dimensional theory can be described in terms of a sigma model into the Hitchin moduli space. So what happens in this case, so I only can tell you what it does in the abelian case, but already there, what used to be just flat connections now becomes something that's twisted by this one duality bundle. So in fact here, A and A bar are the components of the gauge field along the curve, and then our sections of omega 01 on the curve, but twisted by this duality bundle. And so the equation becomes this sort of an equation. In fact, it's not the standard flatness condition for the connection, but something that's twisted by this LD bundle. So it'd be interesting to know what that is for the non-abelian case, and also then, of course, what is the resulting moduli space for that. Okay, so this is now we have a CFT. We only have it for the abelian theory, but still, there's a natural question: can we now construct an AdS3 dual? And then you walk down the corridor to your supergravity friend and ask, well, have they been constructed? And they hadn't been. So we started discussing this. And then you feel like you're a little bit like in this sort of a tournament where people think very differently about the same sort of thing. So, you know, F theorists like singularities, supergravity theorists want everything smooth, many other sort of aspects like this. But so, in fact, it turns out to be relatively straightforward to actually pose this question and to sort of carry through what you know, type of solutions we can find. So we consider type 2b supergravity. We don't have three-form flux, but we do allow for the axial dilaton to vary. The ansatz is an AdS3 times the 7 manifold, and some ansatz for the 5-form flux. So it turns out the 7 manifold has a killing vector, so we can write in terms of vibration over 6 manifold. And now the killing spin equations, if we study them, including this varying tau object, we obtain an auxiliary 8 manifold, which at generic points will look like an elliptic fiber whose complex structure is the axial dilaton fibered over a 6 manifold. And this has to its Ricci has to satisfy this equation here. So that looks very complicated, and we can't really solve it in this way directly. So far, we have only imposed that we preserve 0,2 supersymmetry. If we ask for 0,4, which is the supersymmetry for the Calabi-R3 case, we actually see that M8, this auxiliary manifold here, has to actually be an S2 times an elliptic Calabi-R3 fold. So some Ricci flat manifold Y3, and then the total space becomes the circle fibration here, fibered over the S2, so this gives an S3 times this elliptic Calabi-R. So this is the F3 solution. So we get an AdS3 times S3 times Y3. And the flux actually is determined, is fixed in terms of the Kähler class of the base manifold of this Calabi-R3. So here again, tau is the complex structure of this elliptic curve. JB is the Kähler form. And in fact, we can allow for a discrete quotienting by a subgroup of SU2. So we can actually act with, for example, some ZM subgroup. And that still preserves 0,4 supersymmetry. So the physical compactification space of type 2b string theory would be AdS3 times S3 mod gamma times B2. And B2 is a Kähler surface, and the constraint on it is that it allows for an elliptic vibration to be put on it that's Ricci flat. So in fact, that constrains it to be a Del Pezzo surface, Fn, or a blow-up of these, or an Enriquez. Okay, so this is essentially the solution. It has as I said, in a dual theory, it would be 0,4 supersymmetry, and it's the small superconformal algebra which acts in terms of an SU2 inside the SO4 that acts on the S3. Now you might ask, what is this additional gamma quotient that we can do here? So gamma, for example, equals to Zm, gives, in fact, a very nice interpretation in terms of MKK monopoles. So this S3 mod gamma actually is exactly in the horizon geometry for, say, an F3 compactification with branes on Y3 times Tn with charge M times R11. And so another way of thinking about this is that this is a special Calabi-Yau fivefold compactification of F theory, and M sort of dictates the number of Taubnut charges. Okay, so I didn't bother writing out all the metrics and so on, but this is essentially what the solution is. What we now want to do is compute the central charges and compare. Now, the first thing to do is to look at a leading order central charge using the Brown-Hainaut formula, so C left and C right to leading order. In the solution, plugging it all in, is in fact given in terms of 6n squared m. So n is the number of D3s, and m is the Taubnut charge, times the volume of the base. So the first sort of obstacle comes in that if you're looking at an elliptic Calabi-Yau threefold, the induced metric on the base, if you have some interesting Calabi-Yau with singularities in the fiber, will have a singular metric induced on it. At least that's expected, looking at, for example, the K3 case from the stringy cosmic strings. So that seems to be sort of an obstruction to then compute the volume. Now, we can use sort of a detour and actually circumnavigate this by using sort of some algebraic geometry input. So B2 I can think of as the section of this Weierstrass model that gives rise to this Calabi-Yau 3. And I can compute the volume of this just by volume of B2. It's the integral of the Y3, the section wedged with the pullback of the Kähler form from the base. So omega 0 is exactly the 1,1 form dual to the base of this Calabi-Yau 3. So this is essentially one way of defining what the volume of B2 is without using a metric. Now, in following this up, so I can actually now simplify this expression here further, using that this is the section, and then it's just integral over bj wedge j. And now j is dual to a curve in the base, so you can think of this indeed as just half c dot c in the base. So then the central charge at leading order is 3n squared m times c dot c. Okay, so that was just sort of the warm-up. Now we need to also compute the subleading order ones, which we get from the Chern-Simons couplings of the 7 branes. So C left minus C right is 6n C1 of B dot C. And we can also compute the level of the superconformal R-symmetry, which then determines the right-moving central charge directly, and that comes out as this expression. And this calculation, in fact, depends crucially on having set m equals to 1. In this case, we can actually identify what is the superconformal R-symmetry in terms of gauging that inside the SO4 transverse. So for m equals to 1, we get the following central charges. And then so the question is, how does that compare to, say, what we got from the spectrum? From the spectrum, we got this expression here. Now, the spectrum calculation will have a center of mass mode in it, so we need to subtract that off. And so we get here from C left, we get 2, and here we get 0. And if you now look at the complete AdS, holographically computed central charge, the right-moving charge then matches exactly with the spectrum, and the left-moving charge is then only accurate up to order n to the 0. Okay, so then there's this slight glitch that here we had to actually pick m equals to 1. So the dual brane setup, as I said, will be so the 3 branes, but we also will have to have these additional KK monopoles. The m equals to 1 has the same near horizon as having no KK monopole. That's why m equals to 1 allows us to sort of compare with the n equals 4 calculation, but it would be nice to actually generalize this to all values of m. And for this, it's useful to look at a couple of other cases, in particular the M-theory dual. So one cross-check that we can right away do is looking at the anomaly of the self-dual strings in 6 dimensions. Let me just briefly sort of say this in terms of just showing you the expressions that we get. The general expression for this anomaly polynomial I4 was determined in these papers here. And in our case, this results in the right-moving KR level given in this way, and this matches by this general formula here to the right-moving central charge over here. So we want to actually extend this to general values of m. So we have AdS3 times S3 mod the m times Calabi-R3, elliptic Calabi-R3. That's our solution. And we'd like to know what actually can we say about the central charges, including m. So we use MF duality to map the solution now to M theory. So remember, M theory on elliptic Calabi-R Y is F theory on Y times S1, or type 2B on B, the base of the Calabi-R times S1 with the varying tau. In our case, the S1, which we can use here, is in fact the Hopf fiber of the S3. And so we can dualize along the Hopf fiber, preserving supersymmetry, and then the solution actually in M theory is AdS3 times S2 times the Calabi-R3. And the four-form flux in M theory is given by the volume of the S2, volume form of the S2 wedged with the scalar form of the Calabi-R. So the AdS3 times S2 solution in M theories, they've been sort of classified in this paper, and in fact this falls into the classification. We can think of N and M as now a flux through either an elliptic surface, so this is like these M5s wrapping the elliptic surface C hat, dual to the D3s, and M is the flux through the base, which is dual to the KK monopoles. So in fact, the M5 branes that we're considering here are wrapping an ample divisor, M times the section, B2, plus N times a combination of the elliptic fibers. Okay, so we can calculate in this setup now the central charges either using M5 brane anomaly, polynomial integrating this over this divisor P, like in these papers here, or use the holographic central charges in AdS3 times S2 times Calabi-R3. And so let me just tell you what the result is. So we can extract from here directly the level of the superconformal asymmetry for general M in terms of intersection data on the Calabi-R3. So Cij are just the triple intersections of divisors, and the Ki's are the expansion coefficients of the scalar form in terms of the duals of these divisors, which are 1-1 forms. And the result is now an N and M dependent expression, again, depending on the intersections of the curve with itself and the first Chern class of base. And the central charge is now this expression, which looks somewhat daunting, but if you set M equals to 1, this indeed gives rise to the central charge that we got in the F-theory D3 analysis. So it would indeed be interesting to generalize that analysis in F-theory to include these KK monopoles. Okay, so let me summarize because I'm out of time. And so what we have started is looking at holography with an F-theory, specifically AdS3 CFT2. Then there's a particularly nice setup are the elliptic Calabi-R3s, where we have wrapped the 3 branes in F-theory, which are then dual to AdS3 solutions. So what we're looking at is n equals 4 superangles with varying tau, plus these duality defects, which give rise to 2D chiral CFTs. And dually, we have an AdS solution where tau actually is allowed to take a non-trivial profile. The checks are mapping it to M theory and comparison with various anomaly calculations. So what else is there to do? Well, this is sort of just, I think, a starting point for this type of story. So one thing that I think would be extremely nice is to generalize the spectrum calculation for a non-abelian n equals 4 on curves inside F theory, including such duality defects. Then holographically, we can reduce supersymmetry, look at duals to Calabi-R4, or maybe even 5-folds with 0,2 supersymmetry, maybe non-chiral supersymmetry, etc. There's some interesting related so conceptually related work on AdS6 solutions, dual to 5D superconformal field theories, where also the type 2B solutions are now such that tau varies and has a non-trivial SL2C monodromy. So these are coming from a completely different direction, but also have this sort of behavior. And then, of course, it would be nice to generalize this to AdS5 and maybe generalize this known construction for constant coupling. Okay, thank you.
Thank you very much. Are there any questions?
Ufer has one.
So you mentioned that these theories have both M-theory duals and F-theory duals. So how big does the parameter M have to be for the M-theory dual to be more useful?
Right, so this actually depends on the specific, the thing that I sort of mentioned here, that this object here has to actually be ample. So in MSW, you may remember this, there was a condition of very ample. The AdS solution actually exists for ample devices, and this imposes that actually N needs to actually be sufficiently large. So there's an equation for this I can show you.
More questions?
There's one back there.
Back there.
Hi.
Hi.
Do these CFTs have interesting, relevant, and marginal deformations? And can you look at them with this F-theory construction?
Yeah, that would be interesting. I think this requires actually to generalize this to non-abelian versions of these. As I said, so I think for the bulk theory we understand this construction, but I think the interesting thing is the additional duality defects for non-abelian such n equals 4s. I don't know how to construct those yet. So I think you would have to generalize that first to answer that question.
Any more questions? If not, let's thank Sakura again.